Okay, hello. So good morning, good evening, good afternoon, whenever you're watching this. Today's just going to be a little bit of proof. We covered it in lesson, so if you're in lesson, you don't need to worry about it. But the main idea, let me just share my screen, is that there are two types of proof. So there are statements which have been proven, and we call them theorems. So the most notable one would be this guy here, which is Pythag. And he has a theorem, and statements which aren't proven but we assume are true are called conjectures. And this is a famous one by Goldbach, and it's Goldbach's conjecture, and I would encourage you to have a look at that because it's a really nice idea. So, what is a proof? Well, in the lesson we discussed about what a proof was, and the main sort of idea that we got to was that a proof was essentially logical and structured arguments for statements which are always true. And it should follow a series where someone who hasn't done the proof will be able to understand what is going on via it. And we typically finish a proof with either QED or as required, just something to indicate that we have finished. So the first type of proof, and the main one that we'll be looking at, is proof by deduction. So prove that the difference between the cube and square of an odd number is even. So, in order to do this, we need to first of all define what an even number is. So, an even is going to be something which is a multiple of 2. So, it's a multiple of 2, and that is some awful handwriting. So, I'm just going to, it's going to be something which was times by 2, and we need to prove that the difference between the cube and the square of an odd number is even. So, we can say that an odd number, well, if an even is a multiple of 2, an odd number is going to be a multiple of 2, and then add 1 to make it odd. So we've defined what an odd number is. So an odd number cubed is 2n plus 1 cubed. And if I take away 2n plus 1 squared, I need that to be some multiple of something. I don't know what it is yet, but that's my end goal. Okay. I'm going to work out what this is. So 2n plus 1 cubed is going to be 8n cubed plus 12n squared plus 6n plus 1, take away, and it's going to be 4n squared plus 4n plus 1. So when I take them away, I end up with 8n cubed plus 8n squared plus 2n, and as we were thinking earlier, I want that to be some multiple of 2, so I take out a factor of 2, and I'm left with 4n cubed plus 4n squared plus n, which has to be even because it's 2 multiplied by some value. So I'd encourage you to pause it and write that down. The next thing we're going to look at is, it's still a deduction, but it's given cases. So given that n can be any integer such that n is greater than 1, prove that n squared minus n is never an odd number. So the issue here is it's telling me it can be any integer. So I need to categorize my integers now. So I'm thinking integers can only be odd numbers or they can only be even numbers. So my first case is going to be if the number I pick is even, then n squared minus n is going to be 2n squared minus 2n, which is 4n squared minus 2n, which is going to be a multiple of 2 because it's 2n squared minus n, so therefore even. And my next case, so that was case 1. Case 2 is if it was odd. Sorry for that awful handwriting. Case 2 is odd, so if I had 2n plus 1 squared minus 2n plus 1. So expanding that, I get 4n squared plus 4n plus 1 minus 2n. Well, it's going to be minus 1. Is going to be 4n squared plus 2n, which is 2 lots of 2n plus n, which again would be even. So there I've proved that for any integer, whether it be even or odd, because they're the only types of integers, prove that n squared minus n is never an odd number. Okay. And the last one would be a proof by deduction, but it's using identities. So here we know it's an identity because I've got a triple equal sign. And this just means that I can't now start multiplying both sides by the same thing, because obviously I could multiply both sides by 0, and therefore I would end up with 0 equals 0. So what I have to do is I have to think about this in terms of sides. So I'm just going to have a look at the left-hand side, and I'm going to try and rearrange this in some way to get it equal to 4xy. So my left-hand side is x plus y squared minus x minus y squared. I'm going to expand these, so I end up with x squared plus 2xy plus y squared minus, and it's going to be x squared minus 2xy plus y squared. So when I subtract them, x squared take away x squared is 0, 2xy plus 2xy is 4xy, and then that's going to go to 0 as well, so it's 4xy, and this is equal to my right hand side, so therefore left hand side is equal to my right hand side, which is what is required. So identities, we just simply look at one side and we try and solve it to equal the other side. Okay, I've got 9 questions here. I'd like you to pause it and have a go at these. The only thing I'll notice that this one, I'd like you not to use a quadratic formula, and if you could complete the square, that would be great. So that would be for this question. So pause it now, have a go at these questions. Okay, and the answers, so question 1, 2, 3, 4, and 5, pause it. And question 6, 7, 8, and 9, pause it. Okay, and this leads us on nicely to a different set of questions. So these are proofs with if statements, and all we need to know is we need to prove that if 2 plus 3x cubed is bigger than 80 plus 54x squared plus 27x cubed, then x must be greater than 2. And the way we do this, again, I've got this cubic here, I'm going to expand it, so 2 plus 3x cubed is going to be equal to, well, it's 8 plus 36x plus 54x squared plus 27x cubed. So if I put them equal to each other, I get 8 plus 36x plus 54x squared plus 27x cubed is going to be greater than 80 plus 54x squared plus 27x cubed. So cancelling out, I've got a 27x cubed in both and a 54x squared in both. So that leaves me with 8 plus 36x is greater than 80. If I subtract 8, that gives me 36x is greater than 72. And dividing by 36, I get x is greater than 2. So therefore, if this is true, that means that x must be greater than 2. Is also true, which is what I've got here. Proof by exhaustion questions. Well, if I'm proving that 2n plus 1 squared is greater than 2 to the n plus 1 is true for all positive integers less than 7, I'm going to start off and just choose integers. So when n equals 1, I get 3 squared is greater than 2 squared. 3 squared equals 9, 2 squared equals 4, so I'm happy with that. N equals 2, I get 4 plus 5, 5 squared equals 25, and I get 2 to the power of 3, which is 8, and I'm happy with that. The next one, n equals 3, I'm going to get 7 squared equals 49, and 2 to the 4 equals 16. Carrying on for n equals 4, n equals 5, n equals 6, I'm going to show that all of these are going to be true. So I've done my proof by doing every single scenario that could happen, and that would be exhaustion. So for n equals 4, it's 9 squared is greater than 2 to the 5, which it is because that's 81 and 32. Then I've got 11 squared is greater than 2 to the 6, which is 121 and 64. Then 12 squared is greater than 2 to the 7, which is 144 is greater than 128. But then obviously the next one would be 13 squared is trying to be greater than 2 to the 8, which isn't true. However, this would be for n equals 7 and hence not less than 7. And finally, the last one to note is just about this method called jotting, and essentially prove that any positive integers are x and y such that this is the case. Now, what's important to note about this is that we have two variables. We've got an x and a y variable. So therefore, when I look at this, I'm going to first of all think about just what can I do to this to make it seem like a more logical statement. Well, if I square both sides, I get x plus y squared is greater than or equal to 4xy. What I can do now then is if I expand, I get x squared plus 2xy plus y squared is greater than or equal to 4xy. And it's still not quite a logical statement, so I'm going to take this across. So I get x squared minus 2xy plus y squared is greater than or equal to 0. And now I need to make this something easy to show that this is always going to be bigger than 0. When I factorize this, I get x minus y squared is greater than or equal to 0. So this value here can be either positive or negative, depending on whether x is larger than y. However, we know that any number squared is greater than or equal to 0. So therefore, this statement here and this statement here are basically the exact same thing. So therefore, this is the proof concluded, because it's very logical to assume that any value squared is greater than or equal to 0. So that would be the finish of the proof, and it would also come to the conclusion of my teaching. I did do a counterexample, but the way we would look at this question, sorry, I'm just going to get rid of all the workings out. That was just something we were looking at in class. So for this question here, we're going to think about a value which wouldn't work for this example. So n squared minus n plus 41 is prime for all values of n. Well, if we think about this, if I have a value of n which is equal to 41, what I would end up with is n squared minus 41 plus 41, where these two values are going to cancel out, and therefore all I'm proving is that f41 squared is not prime. Well, obviously it's not, because 41 is a factor, as well as whatever 41 squared is 1, so it's going to have more than one factor. Okay, I'd like you to pause it now and have a look at this question. I've written a little hint for the step question if you'd like to have a go at that, but that would conclude the teaching. So thank you very much.